I run a meetup group in New York City. And one of the things that we do whenever we have a speaker come up, in order to welcome the speaker, is we ask the person to say their name, and we all say hi. Now, one thing is that room over there is really packed, but there's a glass wall here. So I'm going to say, hi, my name is James Powell. And all of you are going to say as loud as you can, hi, James. Loud enough to make all those people be like, what is going on over there? So are you ready?
Yeah.
Do you need to take a breath? Everybody's ready. So I'm going to say, hi, my name is James. You're going to say, hi, James. Okay. I'm going to start the talk. Hi, everyone. My name is James Powell.
Hi, James.
Yeah, they looked over. So there we go. So we're at PyData London. Today is Sunday, June 21st, 2015. If you have any questions or any complaints about this talk, you can follow me on Twitter and tweet at me at don'tusethiscode. If you want to email me, you can email me at james@don'tusethiscode.com. If you want to read my old blog, you can read it at seriously.don'tusethiscode.com. There's a pun, okay? We keep going with this. And if you want to find me on IRC, I'm DUTC on IRTC for Don't Use This Code. And sometimes if that handle is not available, I'm DUTCH for Don't Use This Code, Haas. I'm from Texas. I run the New York City Python Meetup Group. It's the world's largest and most active Python Meetup group. We haven't had an event in a while, but we're going to get started again quite soon. We have a huge data science community in New York. So if any of you find yourselves on the other side of the ocean, please look us up. Come attend one of our events. We have a lot of great speakers, a lot of great organizers, a lot of cool stuff happening in New York. We have things like office hours every Tuesday. We have study groups on Saturdays and Sundays. And we have headline events on Thursdays. I also work with NumFocus to help put on events like the event that we're attending here. We organize multiple PyData events every year. In fact, none of the London local team know this, but if you don't include the Google Day, this is actually PyData 10. And we totally missed out on the branding of this being PyData X, but that's what it is. So we've done 10 PyData events so far, not including the first Google Day that was like 40 people. If you don't know about NumFocus, one of the things that I'm tasked with doing is reminding people what NumFocus is. It's the 501c3, so the United States federal nonprofit that funds projects like IPython Notebook, like Julia, data science projects. We fund NumPy, we fund SciPy. A lot of the tools that you're using day to day are funded by NumFocus. It's also the organization that hosts and organizes and puts on the PyData conference series. This year we had PyData Dallas in April. We have PyData London right here. We're doing PyData Seattle next month. I think we already have 1,000 people signed up to attend. It's going to be a huge event at Microsoft headquarters. And we're going to be doing PyData New York. I don't know if these dates are quite official, but by the time the video comes out, these dates will probably be totally available. So we have these 4 big PyData events every year. And we've also done an event in Berlin, an event in Paris. And there's talk of doing events throughout Europe. There was some talk during this event about doing a PyData in maybe Spain, a PyData in Amsterdam. So you have plenty of opportunities to see excellent speakers like the guy next door. You guys are supposed to like self-deprecating humor. This is...
Cue us in and we'll laugh, mate.
Okay, see, I was telling Emlyn, everybody assumes that American humor must always be backed by a laugh track. So maybe we need that. So, about me, I like to give talks at these events. I speak about things like Python, software engineering, applications to quant finance. I have a finance background, data science, machine learning. These are the areas of my own interest. This year, I've spoken at PyTennessee. I gave a lightning talk at PyCon in Montreal. I spoke at an R conference. I have a friend who I usually invite to speak at Python conferences, so he invited me to speak at an R conference. Got to mix it up a bit. I spoke in Dallas at PyData Dallas. I spoke at the Open Data Science Conference last month in Boston. We're at PyData London here. And if you'd like to see me again this year, I'll be in Seattle for PyData Seattle. I'll probably be at PyGotham, the conference that we're organizing in New York. I'll probably be at PyTexas. I'm from Texas. And then PyData again. So there's plenty of opportunities to see or not see my talks, as you choose. And also ODSC at the end of the year in San Francisco. So just to preface this, some of you may have seen my talk last year on generators. And this is a topic that I have been talking about for a very long time. In fact, one of the very first talks I ever gave was at PyData in New York in 2012. And it was called Generators and Coroutines for Stream Data Processing. I then took that talk and rewrote it and presented it at PyData Silicon Valley in 2013. Then I presented that talk in addition to 2 other talks at PyData Boston in 2013. And then I presented 2 of those talks. I let one of them spin off to my co-presenter. I presented another generators talk at PyData in New York in 2013. I took that talk, and I swear to you, I actually added some new material when I presented it in London. Then I presented it again. I just changed the name for Silicon Valley because I thought, we need something new in here, and I couldn't really put in the effort to do anything but change the name. Actually, I changed all the slides, but we presented it again in Silicon Valley, then in Berlin, then in New York again, and then suddenly this year I decided, let me bring you something fresh. So here you have a brand new talk called Integration with the Vernacular. I presented it at Dallas and here at PyData 10 in London. So this is my 10th PyData talk, or my 10th PyData appearance and my 15th PyData talk. So as you can see, all of you should, for next year, submit a talk to PyData London. They'll accept anybody. That's it.
We have a very low bar for quality.
Yep. So this talk is called Integration with the Vernacular. And it's about the numpy approach. This is not a features talk like generator. As the generator talk evolved, it turned from being something more about this is what it is, these are the features, this is how you use it, talking about code and just going through documentation and things like that. And it evolved towards being a talk about conceptualizations, about modeling, about how you can use this tool in order to structure a program, in order to rethink the way the computations are structured. And as that talk evolved, I realized that what I was most interested in was these high-level conceptualizations of what we're doing when we're writing software. Now I know I'm presenting in front of a data science audience, and for the most part, data science audiences don't really care that much about software or code. It just happens to be what they need to do to get the job done. And for many data scientists, if they could do analysis by just banging 2 rocks together, they would, because they don't care about code. They care about the data science. They care about machine learning. Still, I would assert that there's a lot of importance in terms of how the tools are used, how you structure computations around the tools, about understanding how to build actual pieces of software, these artifacts that we dismiss. Oh, it's just writing software. I think that's actually a very important thing. And I think that's a science and an engineering unto itself. This talk, like many of these high-level thought leader type talks, this talk is supported by an analogy. But rather than belabor mathematical analogies, of which I think there are many, I decided to belabor an entirely different and substantially more absurd analogy. There's a lot of editorializing in this talk too. I will say, however, that as a serious note, I would like to convey to the audience that engineering is a fundamentally human approach, and that everything about this talk, everything that I'm trying to convey to you, is that our job, independent of whether we're software programmers or quants or data scientists, our jobs are usually to generate some artifact that supplants or that supports some human process. And that there's a lot of work that goes around generating that. I mean, we have application of theory, but there's also a lot of consideration about political consequences in terms of how the organization internally works. There's a lot of thought about how code evolves over time within an organization. There's a lot more to it than just the raw computer science. Fundamentally, this talk is about creating a language or a framework for understanding and discussing software development from an engineering perspective. We could, for example, say that when we write software, we're constructing an algebra. You can think that a piece of software is really some domain in which you have some qualifications on the input data and some qualifications on the codomain that has some certain properties that you assert over the domain, and some certain relations and operations that you assert over objects in that domain, and then you apply it to objects you've never seen before. And if you've written that software well, those properties still hold. So for example, when you learn math in school, you learn math over numbers that you can fit into your head. And you never ask, well, I learned that, for example, addition is associative, but what if I give it really big numbers? Presumably when we write software with some inputs in mind, and then we apply it to inputs we've never seen, and we assume that certain properties and certain operations that we've encoded still hold on inputs we've never seen. That's what I think software really is. And that's a mathematical analogy we could take. Instead, what I wanted to share with you is an analogy that has really stuck with me, that was born in my previous life. So I actually have an engineering background, but I did my undergraduate degree in Asian studies. And so what I'm going to provide to you is a very interesting analogy that stuck with me that describes and conceptualizes something that I've seen when using numpy. A very important qualification is, I'm going to criticize numpy a lot here, but numpy is actually really great. It's a very useful tool. It's something that actually gets real work done for a lot of people. But it's a tool that was born many years ago in what you might consider to be the pre-modern era or the pre-contemporary era. So just one last warning, this talk is totally inscrutable. So let me start by going back to 1911. So in 1911, there was the May 4th movement in China. Remember, China was an imperial state until 1911. From some 2000 BC until 1911, it was ruled by a series of imperial dynasties. And in 1911, there was this first move towards republicanism, towards actually destroying the dynasties and forming a state as a modern political entity. Well, the May 4th movement is this mix of a political and social and literary movement. In 1919 in Beijing, there were a group of authors that are very closely associated with the May 4th movement. Some of the authors on the screen, Lu Xun, Mao Dun, Lao Se. And if you read their works, or if you're familiar with any sort of contemporary Chinese literature, rather modern Chinese literature, these names come up. And one thing that really typified this literary movement was the use of the vernacular. And this is something that is a little bit odd to an English-speaking language. But if you look really closely, prior to 1919, any literary Chinese was written in classical Chinese. It was written in a dialect that nobody spoke. So just imagine if, until 1919, everybody who's writing anything in English wrote in Shakespeare's English. And that's the situation that they had in China prior to the May 4th movement. And these authors, amongst others, promoted the use of the vernacular, promoted the use of the language that people actually speak when writing things like short stories or when actually putting pen to paper. When we talk about classical Chinese and literary Chinese, there's many different terms and many different terminologies and many different things we can talk about. But one thing that typifies classical Chinese is the use of idiomatic expressions. And this is something that we see in very formal dialects of English as well, in acrolex of English as well, which is set phrases that we don't really have any way to break down, that just percolate down to us. And this is a very, very common thing in Chinese, and it's something that you see a lot. You have these 4-character idiomatic expressions. And these 4-character idiomatic expressions are something that originated in texts that were written hundreds of years ago and are integrated into everyday speech. And they're very poorly integrated in everyday speech. And one very common example of this is falling leaves return to the roots. This is a very common idiomatic expression that any speaker of Chinese will know. In Chinese, it's 落叶归根, and it means, it's usually used to metaphorically refer to things like when you get older, you want to retire back to where you came from, just this notion. But the very interesting thing about this idiomatic expression, despite any speaker of Chinese having run across this, and maybe even used this in everyday speech, is that if you look at where it came from a text from a very long time ago. It came from a Song Dynasty text called The Records of the Transmission of the Lamp. And I actually looked it up, and it's very easy to find this on Google by searching these phrases, and you can see, here's the actual phrase that it came from. And when you look at the actual phrase where it came from, you can see that, and here's the actual text, and it's a discussion between two people about this. But when you look at it, you can actually see some very interesting things. We have a situation in which some very common idiomatic expression that somebody is using in everyday speech originates in a text that nobody's ever really read, and nobody's really ever sourced from directly. And it's just part of the language. It just appears there. And this is somewhat familiar to us, but not really. And the closest that we get in English is Shakespeare. And how Shakespeare has permeated, how Shakespeare's language, this is very appropriate for our audience, but how Shakespeare's language has permeated the use of English. So North by Northwest. In our media, we have movies, we have books that draw from Shakespeare. North by Northwest, What Dreams May Come, Murder Most Foul, these are all phrases from Shakespeare. Star Trek VI, The Undiscovered Country, is also part of it from Shakespeare. But the weird thing is, if you look at this original phrase in Chinese, you can see that what we say in modern Chinese is 落叶归根, the falling leaves return to the roots. But in the actual original phrase, where it came from, these two characters are swapped. It's actually 叶落归根, And this is it's not a terribly uncommon thing in Chinese to have these kind of character swappings, but it's interesting that you have this phrase that exists and this slightly more compatible to how you think about it in a modern sense actually originated as a completely different phrase. And it comes out as, you can see that this has been divorced from its original context. You have this way of speaking that is totally unrelated. Nobody knows where it came from. Nobody knows the original phrase. Whenever I provide, in the last 3 talks that I've given, I've spoken to people who had background in classical Chinese, and even they are surprised to say, oh, actually, that's how the phrase originally looked. So you can see that we have this weird separating from the original source text. We do have this a little bit in English. So Shakespeare generates a lot of this. So we have foregone conclusion, which came from Othello. We have sea change, which came from The Tempest. We have to send somebody packing, which came from Henry VI. We have a number of these that we don't even unpack, right? We don't even think, what does it mean to send somebody packing? What does it mean, a sea change? These are metaphors that come to us, but we never really interrogate where they came from. We just try to integrate them into speech, and for the most part, it comes out as being fairly well integrated. However, the interesting thing about Chinese is these are very poorly integrated with the Chinese vernacular. So if you take a phrase like, this proposal is not guaranteed to go through in Chinese, and this is what it would be in Chinese, you'll see that there's actually a 4-character proverb right here. And this conveys the meaning of guaranteed. Now, one thing to note is that Chinese as a language is very isolating. It lacks an inflectional morphology, which means that as you'd expect, you can't really change the character. So when you want to build Chinese, you don't have verb inflections, you don't have anything like that. You just kind of put the pieces together. And so what that allows us to do, at least for a non-Chinese speaking audience, is to take a sentence like that and actually break it down word by word. So for this sentence, this literally means this means proposal, this means is not, this means guaranteed, and this means to go through. Well, this thing right here is a 4-character proverb. And it's just integrated right into that as an adverbial phrase, right? And you can see we have this marker here, which indicates that it's an adverbial phrase. But you have this 4-character proverb smacked right in the middle of a sentence that comes from some source that nobody's ever learned, that just screams at you. It's an indivisible entity that just screams at you, this is not modern vernacular. This is not just a word. It's not just an adverb. It's a set phrase with an idiomatic meaning. And if we actually look it up, we can see it comes from some source text. And the source text that it comes from, it's not even written this way. It's actually written completely differently. The last 2 characters are completely different. So the idiom that we're using, that we attribute to this original source text, isn't even what was in the original source text. So we have this very weird integration with the vernacular. Well, this is something that has stuck with me for a very long time, because it's a very odd thing. It's a very odd thing to, in Chinese, say a sentence and have this kind of weird ancient language pop up in the middle of it, and then to immediately be drawn to that as a set phrase, and to have no way to break it down or to integrate it into that. And when I started to really start using NumPy heavily, I started to get the same sense. The programs that I was writing had some portion that was vernacular Python, that was idiomatic Python, that was, the kind of Python that, when I read PEP 8 that I'm supposed to write. And then suddenly, in order to write good NumPy code, I'm suddenly combining these indivisible objects from this very ancient style of communication. For some background, for those of you who don't know what NumPy is, it is, of course, the premier library in Python for numeric computing. It's the basis for tools like SciPy, for Pandas, for scikit-learn. But fundamentally, what it is the ND array. If you really look into NumPy and you try and see what it's all about, you might say, well, it's a combination of numerical algorithms and some data structures like matrix or inverses. Or you might say it's things like FFT and these algorithms and these approaches for signal analysis. But really fundamentally, NumPy breaks down to just the NumPy ND array. There really is, it's NumPy ND array and then a bunch of stuff on top of it. And a bunch of additions that are useful for specific use cases, but it really comes down to this ND array. And the ND array is just some structure that allows you to broadcast operations. So when you take this, you multiply by 10, it broadcasts that to every element. It's some structure that allows you to do things like fancy indexing. It's some structure that has a specific machine type. So now we're getting somewhere kind of weird because we've never talked about machine types in Python, right? Nobody ever says, oh, we have a number here. Is this an int or a long? Has anyone ever wondered if you're using in Python 2 an int object or a long object? They're both separate objects, right? But you have automatic promotion. And for the most part, if you're doing things in heavy loops, you might wonder, why is this loop slow when the numbers get a little bit bigger? But even in Python 3, there's no separation between the in object and long object anymore, right? So we're beginning to worry about things in NumPy that are completely foreign to people who are writing normal Python code. Not only is this this is a machine type. It's an int64. It's not even saying int versus long. It's telling you the exact number of bits in that int, right? And in Python 3, look, they're going in the opposite direction, where we're no longer really distinguishing between floats and integers, right? You do your division, and division automatically generates a float for you, because we're trying to create this more human-friendly numerical system, and we don't want to have to deal with, well, 3 divided by 2 is actually 1 because it's truncating, because that's what happens in C when you have ints truncating, and that's how the operation is defined on C. Python's moving the opposite direction, whereas NumPy is still stuck in this world in which you worry about details like the machine. Now, of course, the reason you do that is because this is what allows NumPy to perform the way it does. NumPy is a constrained computation environment. NumPy is an environment in which you say, NumPy, I'm going to follow your rules, and I'm going to do a bunch of stuff for you, like I'm going to tell you exactly the machine types I want to operate on. I'm going to assert certain things to you implicitly, not just the types, but I'm going to implicitly assert things like the entities being independent of each other. So think about an NumPy ND array. It's just a big block of memory, and the elements inside of it are basically memory managed by NumPy, and the operations on them are completely defined by NumPy. So certain things like interrelations between the entities are not expressible in NumPy. You can't say this is an array, and this number in this array depends on this number in this array here. That all has to be done by mechanisms outside of NumPy. And as a consequence, by constraining yourself into this computation domain, NumPy could do things potentially like automatic vectorization. When you do a broadcasting on NumPy, there's no reason why NumPy can't multiply all those numbers in parallel, because it knows that there's no interdependencies there, because you've given it this very restricted domain in which certain assumptions can hold. And so, for example, what you can do with NumPy is you can take this restricted domain and you can perform operations on them. You can take these high-level building blocks in this restricted domain, you can perform operations and generate meaningful computations. So here we have something like computing volume-weighted average price. A very trivial, very basic exercise you might do in Python. Rather in finance. You have a set of dates, a set of closes, and a set of volumes. And in NumPy, to express this computation, you have an average function, which is this big indivisible building block, and you have no idea what it really does under the covers. You give it the closes, and you give it the weights, and it goes off and it does all these computations. And how it implements those computations, you don't care. It's almost declarative in a sense. And whatever NumPy does internally, it doesn't matter. In fact, there was a talk yesterday by one of the PyPy developers, Romain, about how he talked about integrating with NumPy by embedding a CPython interpreter into PyPy. And that's actually probably a fairly useful thing you could do, because as long as all the computations stay within NumPy, it's good enough. So you could have all your computations stay within your host CPython interpreter, and then once you need a result, you just have it cross the interpreter boundary back into PyPy. Well, that's the style of writing that we use for NumPy. We have this happen a lot in NumPy. If we want to do something like an exponential moving average, it would just be the exact same thing. We'd take a convolve function, and we'd take our two inputs, and we'd construct these computations by these large building blocks, and all of the real details of what the computation does internally are handled by NumPy. This is a distinct mode of computation, because there are other computation styles or other methodologies for that, that are a little bit more integrated. One example of them is what you may see, these kind of graph computing environments. And what happens with these graph computing environments is there's a desire to not have to bend people to the style of, well, I'm going to do all of these manipulations with these numbers, and then I'm going to get them ready for NumPy. I'm going to stick them to an ND array. I'm going to do the operations of the ND array, and then pull them out the other side. Instead, we want to integrate that into the rest of our software code base. So you end up with things that look like this. You have, for example, to calculate the market value of a portfolio, you have some class that represents some node in the calculation. And that total portfolio value is the sum of the individual values for every position. And then for each position, that's another node in this graph. And the value of it is its size times its price. You assume that everything's linear. And then for that position, maybe it's a bond. So you say, the price is a dirty price, and the dirty price is the clean price plus some accrual. And you construct this node of the computation, and then you can do some neat things with that, because you can say, oh, instead of memoizing, we can just say, if we want to do something like perturbative risk, we can identify exactly the nodes which change, and then recompute without having to recompute things which aren't affected by these small perturbative changes to the leaves. But it's a very different approach, because when you start to look at this code, you'll see that in many cases, there's a desire to integrate these computations with the rest of the application, with the rest of the environment. So in our bond class, you won't only have a price and a dirty price, but you'll start to have things which don't even relate to the computation. Like you'll have the registration type. Whoever's calculating the price of the bond doesn't care if it's public or private. That's a detail that somebody in settlements cares about. This is a detail that maybe one of the traders cares about. But given a specific price for the bond, the computation is really completely separate from that. In fact, think about how many domains where almost all of the work in providing a computation for that domain just devolves to some matrix operations. And when you're dealing with those matrix operations, you don't even think about the units on the matrix operations. Just do this decomposition, do this multiplication. There, that's the result. And that's more relatable to the NumPy approach than this integrated development approach, where you try and say, well, let's try to holistically model this object in a very naturalistic fashion, and also layer the computations into that. Unfortunately, one consequence of this constrained approach is that NumPy does not integrate very well into idiomatic Python. Bear in mind, NumPy was created before you could even say an idiomatic Python existed. What we consider to be nice about Python, things like decorators, things like generators, things like descriptors, things like the class structure, didn't really exist until fairly recently. Things that make Python more than just a wrapper on top of C did not exist until fairly recently. And as a consequence, you could perhaps attribute NumPy's poor integration into Python to it preceding the evolution of these things in Python, right? But I'll show you some very specific conflicts. One very specific thing is if you read Pepe, they say, write your code like this, don't write your code like this. They say, if you want to see if a sequence has elements, you do if not sequence, not if length sequence. And fine, that's perfect in Python. Here's a little piece of code. If you want to see if this is empty, you say if XS. And the first time you try this on a NumPy ND array, what happens? You get this obscure error message, the truth value of an array with more than one element is ambiguous. Use any or all. And what does this mean? Well, it means that trying to determine truth or false on this is trying to broadcast that. You end up with a bunch of truths or falses, and you have to see if all of them are true or all of them are false. And what it turns out is if you wanted to have a piece of code that could interact with both a Python list and a NumPy ND array without having to know what they are, just saying these are abstract iterables, abstract container types, you'd actually have to write it in this fashion. This is the only way that you could have it transparently deal with both a NumPy list and a Python list and a NumPy ND array without having to know either one. Except this is explicitly not idiomatic Python. You're told do not write your code in this fashion. But it goes a little bit deeper than that. NumPy even has these weird boundaries where it interacts unexpectedly with standard Python mechanisms. For example, we're all familiar with generators. In fact, I've given somewhere between 73 and 422 talks on generators. But the thing is, when you stick a generator into NumPy ND array, you get this. And you can make the argument that it may be ambiguous what you mean when you put a generator into a NumPy ND array. And that there's no good choice. And I'll accept that, and I'll say maybe there is no good choice. But you're still going to be a little bit surprised when you try and stick a generator into NumPy ND array, and it gives you an array with one element and then elements of generator. You're going to be a little bit, what is this? You'd expect it to at least try to exhaust the generator. And you might say, well, and you can understand, well, maybe we don't know if that generator is exhaustible, and there's many arguments you can make for why it is this way, but you're still going to be surprised. And you're still going to find that integrating code that uses generators and code that uses NumPy is not very fluent. The NumPy style doesn't interact with rich Python objects either. So one example of that is NetworkX has a very nice thing where if you construct a graph in NetworkX and you want to do things like add weights to the graphs, you add a keyword argument and you can add weights to these graphs. And then you could do things like you could do Dijkstra's algorithm, and Dijkstra's algorithm can take into account those weights, and you can attach a little bit of additional associated information with this structure that NetworkX is itself maintaining for you. There's not really an equivalent for that in NumPy. For example, if you wanted to write a video game and that you wanted to use NumPy to very quickly perform computations on the monsters in your video game, you'd have to take those monster objects that may include some other details that are necessary for the video game, like their hit points and their damage. You'd have to extract each of those individually into NumPy and DRA, perform those computations in NumPy, and then get them out the other side. Because you don't want to put a Python you probably don't want to put a Python object in NDArray. You won't get any benefits from that. In fact, I'll show you that there's some very dangerous things that can happen. But also, you lose the ability to add additional information on top of the limits of what NumPy can itself model. So one very common example is in Python, we want to sort a list. Say we want to sort this list by its absolute value. In Python, we have a very, very nice, very idiomatic way to do it. We pass it a keyword function, and suddenly this list is sorted by its magnitude. So you can see, independent of the sign, the numbers are sorted. How do we do that in NumPy? Well, we have to go back to our Schwartzian transform, our decorate, sort, undecorate to do it. Because there's no equivalent in NumPy. In fact, in NumPy, what we have to do is you have to take this array, put it into a different domain by broadcasting absolute value over that, and then bring it back into our original domain using argsort, and then fancy index on that. So you can see we have to actually do a domain transformation to do something as simple as sorting a NumPy ND array by some arbitrary predicate. And there's no API for that. And this is literally a Schwartzian transform. You can see it's a domain transform to go from this restricted domain that NumPy provides to a domain that is amenable to the computation you want to do, and then back into the original domain. As opposed to idiomatic Python, which is just, I mean, they'd say this is absurd. Let's just write a keyword function and we can sort by anything we want. We can add, or we're given hooks to model that. I don't have slides for this, but another conversation came up yesterday about the limits for overriding D types in NumPy, and how there's no hooks for implementing custom types and doing NumPy computations over custom types. And if you're interested in that topic specifically, please talk to Jeff Reback, who's in the audience. He was the originator for this very, very useful point that I think really drives home how NumPy is just kind of this weird little wart, very useful, but weird little wart that sits in the middle of what we're supposed to consider idiomatic Python. One thing that we can do with Python is we can do things like nice fancy indexing. Except if we try and put a rich Python object like a dictionary into it, it totally breaks down, right? The NumPy has no way to model the computation using item getting, right? There's no way to figure out how to do fancy indexing with that. And so you end up with what's originally a very nice syntax for dealing strictly within the NumPy domain. You can do 0, 0 strictly within the NumPy domain and get exactly that element. There's no way for NumPy to model the computation of 0, 0 where it does something on top. It does something through the NumPy domain into a less constrained Python domain. And in fact, one thing I wanted to show to you before I finish up is there are even weirder corner cases. So I wrote this script on a whim a couple weeks ago. And what it does is it takes a command line and it runs it with ulimit until it stops failing. So it tells you the minimum amount of virtual memory that you need to successfully get an exit code of 0 from some program. And I use this to analyze how much memory a Python program needs. So I run a Python program, figure out what's the minimum amount of memory it needs, then I'll run things in loops and I'll see, is the garbage collector operating correctly? And so if you do that for a piece of code that looks like this, it creates 2 NumPy ND arrays, creates a circular reference between the 2 of them, and then sticks an extra Python object in one of them, and then garbage collect it, what you'll see is that this will run 2 times and then fail. If you have a circular reference between 2 NumPy ND arrays, and one of those ND arrays contains a Py object, when those 2 ND arrays get garbage collected, they will not garbage collect the additional Python object. There's a memory leak here. And you can see in this case it's a fairly serious memory leak, because even with 113 megabytes of memory, this falls over pretty quickly. And the reason for that, there's certainly a reason for that. I mean, I'll show you the same case before I show you the reason for that. The same case with a normal Python array, and you can see it just runs forever. Just runs forever with a normal Python array. So this is a memory leak in NumPy. It's not a very serious memory leak, because I don't think a lot of people are sticking pure Python objects in ND arrays. There's not a lot of benefit that you gain from it. And so nobody's really put the time or effort into looking to try and fixing this. And the cause of it's very simple. The reason for this is if you look into the code for the array object, they don't implement TP traverse or TP clear. So when the garbage collector tries to collect a NumPy ND array, it doesn't then collect everything the NumPy ND array has a reference to. So it's a fairly small thing. There's probably a reason why they didn't implement this, because it's a fairly low-hanging thing. But what you can see is that even the simplest thing of embedding pure Python objects in an empty array is awkward. It's unusual. It kind of breaks. And so this is, when I started to really start using NumPy very heavily, I was like, this is very similar to the feeling that I get in Chinese when I'm dealing with these idiomatic expressions. I have two languages, pure Python and NumPy, and they can coexist, but it's very obvious when I see both of them, and I'll see a piece of code and I'll say, okay, this is the part that's a pure NumPy code, and this is the part that's a pure Python code, and they don't really intermingle, and there's no way to cross that boundary, and there's a domain transformation necessary in order to go from one style to the other. So I hope you enjoyed this very belabored analogy. This was integration with the vernacular. I'm James Powell, and we're at PyData. Thank you so much.